Welcome back to Mechanical Engineering Made Simple, Legends. Lesson 1, Thermodynamics. I'm your host. Let's uncover what the textbooks only hint at. Marcus Aurelius taught that the obstacle is the way. In thermodynamics, energy itself is the obstacle we must respect. The first law tells us energy is never created or destroyed, only transformed. The second law reminds us every transformation creates waste and increases disorder. Heat engines, refrigeration, even the warmth in your own body all obey these quiet, unbreakable rules. School gives you equations. Life shows why perfect efficiency is impossible and why that truth frees you. Stay with me. We turn these natural limits into wisdom and power. Class, en casa.
Man, it really is the great truth of our field, isn't it? And if we're really going to master this, we have to kind of drag all that theory out of the pristine textbook and, into the harsh, unforgiving light of reality.
Yeah, exactly.
Because we're dealing with factual mathematical truths here, the stuff that governs every single physical system on this planet. There are no idealized fairy tales about machines that run perfectly.
Right, no unicorns.
Exactly, no unicorns. If you are designing the pipeline running under a city or, the high-pressure compressor stage of a jet engine that's keeping a plane suspended at 30,000 feet, you are essentially fighting a war against physics.
You really are.
And to win that war, or honestly, just to break even, you have to understand the weapons the universe uses against you.
Which is exactly the mission of today's deep dive.
Yeah.
We are getting into the absolute bedrock, the first law. Now, pretty much everyone who has ever sat through a high school science class can regurgitate the phrase, energy is conserved.
Oh, sure. Everyone knows that one.
Right. It cannot be created. It cannot be destroyed. But let's be real for a second. If you walk into a design review for a 500 megawatt steam turbine and your only contribution is, well, guys, energy is conserved, you are going to be laughed right out of the room.
Yeah, you're packing up your desk that day.
Exactly.
Yeah.
We need to look at how that philosophical concept actually applies to complex machines moving massive amounts of high-pressure fluid.
Yeah, that phrase is a nice philosophical starting point, sure, but it completely lacks the teeth required for actual engineering.
So how do we give it teeth?
Well, to give it teeth, we have to define our boundaries. So let's start with the simplest case, a closed system.
Okay.
Imagine a heavy steel box, just a solid box. No mass can enter and no mass can leave. The only things that can cross the boundary of that box are heat and work.
Right. So like if you put a blowtorch to the box, you're adding heat.
Precisely. You add heat, and if the gas inside gets hot, expands, and, say, pushes a piston outward, it does work.
Okay, so keeping a strict accounting of that box gives us the most basic mathematical form of the first law.
Yep.
Which is the change in the total internal energy of the system equals the heat supplied to the system minus the work done by the system.
That's the one.
So if we write that out, we say dE equals dQ minus dW.
Exactly. It's a strict ledger. The dE is your balance. The heat, dQ, and the work, dW, well, those are your transactions. But here is the critical distinction. And honestly, this is the first major pain point for mechanical engineers. We rarely, if ever, deal exclusively with closed systems.
Because machines flow, right?
Right. If you are working on turbines, compressors, pumps, or, aircraft engines, you are dealing with open systems. Mass is constantly rushing in and mass is constantly rushing out.
So you can't just look at the heat and the shaft work.
Yeah, you can't. You have to track the energy physically carried into and out of the machine by the fluid itself.
And that physical reality forces us to introduce a property that's, it causes endless confusion. Enthalpy.
Oh, yeah, enthalpy.
I remember just sitting in lecture halls, staring at that word on the board, wondering why internal energy just wasn't enough. Like, why invent a whole new thermodynamic property just for open systems?
A lot of students feel that way.
But enthalpy isn't just an abstract math trick, right? It represents a physical struggle.
It absolutely does. It is the ultimate workhorse property of fluid mechanics. Enthalpy, which we denote with the lowercase letter h, is defined as the internal energy of the fluid, U, plus the pressure of the fluid, P, multiplied by its specific volume, V.
Okay, so H equals U plus P times V.
Exactly.
Let's break down the physical reality of that equation, because just reading the variables doesn't really do it justice. The internal energy, the U, that's easy to visualize.
Right, that's just the microscopic kinetic energy.
Yeah, it's how fast the molecules are vibrating, how hot the steam is. But that second part, the P times V, that is what we call the flow work.
Yes, the flow work.
So imagine you are a single packet of fluid. Let's say you're a cubic inch of high-pressure steam.
Okay, I'm with you.
You are trying to enter the main inlet pipe of a massive power plant turbine. But that pipe is already jam-packed with other steam at incredibly high pressure. You can't just casually stroll in.
You'd get bounced right out.
Right. You have to physically shove the fluid that is already in the pipe out of the way to make room for your own volume.
That is a brilliant way to visualize it. You have to perform mechanical boundary work just to enter the control volume.
Yeah.
You are pushing against the pressure of the environment, the P, to insert your specific volume, the V. That shoving, that requires energy.
I always think of it like trying to get onto a crowded subway train in Tokyo at rush hour.
Oh, man, yeah.
You aren't just bringing your body mass onto the train. You are expending actual physical calories, shoving people aside so your body can occupy space inside the car.
That's perfect.
That shoving effort is the flow work.
And because mass is continuously entering and leaving an open system, that flow work is continuously being performed. The fluid entering does work to get in, and the fluid leaving does work as it pushes its way out into the exhaust piping.
So it's a constant process.
Exactly.
Yeah.
Therefore, when we write the energy balance for a continuous steady-state machine, which is what we call the steady flow energy equation, we don't use internal energy. We use enthalpy.
So let's lay out that steady flow equation for the listener. We take the heat transfer rate, subtract the work transfer rate, and that must equal the mass flow rate, which we call m dot, multiplied by the total change in energy of the fluid from the inlet to the outlet.
Yep, that's the core of it.
And that total energy is made up of three things, right? The change in enthalpy, the change in kinetic energy, and the change in potential gravitational energy.
That is the complete picture. But before we move further, we really must address the sign convention in that equation.
Oh, the signs.
The heat transfer minus work transfer part. This is notorious for tripping up engineers, especially when they are writing code to model these systems.
Let's use a bank account analogy to clear this up. But we have to clarify who actually owns the bank.
Right.
So think of the fluid's enthalpy as the checking account balance. Heat and work are the deposits and withdrawals.
But you have to remember, the bank is operated by a 19th century industrialist. You see, the classic thermodynamic sign convention was established during the Industrial Revolution. The entire reason these pioneers were studying thermodynamics in the first place was to build better steam engines.
They just wanted power.
Exactly. Their singular goal was to get useful mechanical shaft work out of a machine. Therefore, they defined output work, the stuff they wanted, as a positive number.
Right. So heat added to the system is a deposit. It's positive. The energy goes up.
Yep.
But work done by the system, work leaving the control volume to, say, spin a generator, is also defined as a positive number in the math.
Which seems counterintuitive at first.
Yeah, because even though that work acts as a withdrawal that lowers the fluid's remaining energy, the equation uses a minus sign for work, meaning a positive work output correctly results in a subtraction from the fluid's total energy.
Exactly. So if you are designing a gas turbine, which is a work-producing machine, the work term is positive. The machine is delivering power to a shaft. But if you are designing a gas compressor, a work-absorbing machine, the work term must be negative. The external environment, like an electric motor, is forcing energy into the fluid to compress it.
Okay, that clears up the heat and work. But I really want to talk about that last term in the steady flow equation.
Yeah.
The change in potential gravitational energy.
Oh, boy.
Right.
Yeah.
I've seen junior engineers run incredibly complex calculations to figure out the exact change in elevation between the inlet manifold of a gas turbine and the exhaust duct, trying to nail down the gravity times height term, the G times Z.
And this is where theory meets practical engineering wisdom.
Please save them some time.
In the real world, you learn to ruthlessly ignore that term unless you're designing one very specific type of machine.
Which is?
Well, the energy associated with a gas dropping 5 or 10 feet in elevation is infinitesimally small compared to the massive, violent changes in enthalpy and kinetic energy happening inside the turbine stages.
Right, it's just nothing.
For gases and vapors, we universally drop the potential energy term completely. It is a rounding error that only clutters the calculation.
So the only time you really care about gravity is if you are building a hydroelectric dam.
Precisely. If your working fluid is heavy liquid water, and the entire principle of your machine relies on a 300-foot drop in physical elevation, then yes, potential energy is your primary driver.
Makes sense.
But if you are dealing with air, steam, or refrigerants flowing through turbo machinery, just forget gravity. Focus entirely on the enthalpy and the velocity.
Okay, so the first law tracks the energy. It's the meticulous accountant making sure every joule is accounted for between the heat, the work, and the enthalpy.
Right.
But as we all know, just because you have money in the bank doesn't mean you can spend it however you want.
Definitely not.
There are heavy taxes, and the universe never, ever forgets to collect. That brings us to Section 2, the unbreakable limit, the second law of thermodynamics, and the concept of entropy.
Yeah. If the first law is the accountant, the second law is the taxman. And let me tell you, the tax rate is brutal.
It really is.
The first law alone implies a perfect symmetry, right? It implies that we should be able to convert heat perfectly into mechanical work and then work perfectly back into heat, running machines endlessly with 100% efficiency.
Perpetual motion, basically.
Exactly. But the second law steps in and shatters that illusion. It dictates that perfect efficiency is physically impossible. Every single real-world process, without exception, creates waste, degrades the quality of the energy, and increases the overall disorder of the universe.
See, I always hear entropy explained as disorder, like a teenager's bedroom getting messy.
Oh, I hate that one.
Me too. Honestly, I've always hated that analogy. It feels completely disconnected from engineering. When I'm designing a multi-stage compressor, I'm not worried about my molecules forgetting to fold their laundry. I want to know the actual physical mechanism of this loss.
And you are right to hate that analogy. It is a severe oversimplification. For an engineer, it is much more accurate to think of entropy as a measure of irreversible dispersion.
Irreversible dispersion. Okay.
Imagine you carefully pour a drop of black ink into a glass of still water.
Okay, visualizing that.
Initially, you have a highly organized system. Pure water here, pure concentrated ink there. But within seconds, the ink disperses. The thermal motion of the molecules spreads the ink uniformly throughout the glass.
Right.
Now ask yourself, what are the odds that those ink molecules will spontaneously, on their own, gather back together into a single, perfect drop in the center of the glass?
Statistically zero. It's impossible.
Exactly. The energy in the glass didn't change. The first law is satisfied. But the arrangement of that energy is permanently altered. The process is completely irreversible.
Because to unmix that ink, you would have to intervene, right? You'd have to build a complex chemical separation plant, consume external electricity, and do massive amounts of work.
Precisely. In thermodynamics, the mathematical expression of this irreversible reality is the inequality of Clausius.
Okay, let's get into the math of it.
It states that for any system undergoing a thermodynamic cycle, the integral of the heat transfer, dq, divided by the absolute temperature, T, must be less than or equal to 0.
And that less than or equal to is the dividing line between fantasy and reality.
Correct. If a process is a theoretical perfect ideal, which is what we call a reversible process, that integral equals exactly 0.
Right, the fantasy world.
In reversible fantasy world, there is no fluid friction, no turbulent eddies, no heat leaking through the casing. You could theoretically run a turbine forward to get 100 megawatts of power, and then use exactly 100 megawatts to run it backward as a compressor, returning the fluid and the universe to their exact original states.
But unicorns don't exist. Reality is irreversible.
Exactly.
And for any real process, that integral is strictly less than 0. This mathematical deficit introduces the property of entropy, denoted by S. Because processes are irreversible, the total entropy of the universe always increases. Entropy is always generated. It is never destroyed.
That's the cold, hard truth.
I do want to pause on a crucial detail you mentioned, though. Dividing heat transfer by absolute temperature. If you try to calculate entropy using Celsius or Fahrenheit, your numbers will be complete garbage. Why is that distinction so important?
Because thermodynamics is fundamentally the mathematics of molecular motion. 0 degrees Celsius is just the temperature where liquid water freezes into ice.
Right.
It is an arbitrary benchmark based on one specific substance at Earth's atmospheric pressure. The molecules in ice are still vibrating. They still possess thermal energy.
So they aren't at 0 energy.
Exactly. If you divide by an arbitrary scale like Celsius, you can end up dividing by 0 or dividing by negative numbers, which mathematically breaks the entropy equations entirely.
That makes sense.
You must use an absolute thermodynamic temperature scale. Kelvin in the metric system or Rankine in the imperial system. 0 on these scales represents true absolute 0. It is the theoretical rock bottom limit where all microscopic molecular motion completely ceases. It is the true 0 of energy.
So we know entropy always increases because of friction and heat loss. But again, how does a mechanical engineer actually use this? How do we quantify the pain this causes us?
This is where we introduce one of the most sobering, powerful equations in all of engineering, the Gauss-Dodala theorem.
Oh, yes.
This theorem translates the abstract concept of entropy generation into hard financial reality. It states that the rate of lost available work, which engineers call exergy destruction, is directly proportional to the rate of entropy generation multiplied by the ambient temperature of the environment.
The equation is W lost equals T0 times S gen.
Yes, that is the literal invoice for your wasted potential. Let's say you have a high-pressure steam pipe and you didn't insulate it properly.
All right.
Heat leaks out into the cold ambient air. That heat transfer across a finite temperature difference is highly irreversible. It generates entropy, S-gen.
And the Gauss-Total theorem tells you exactly how many kilowatts of useful, money-making mechanical power you just permanently destroyed.
Exactly. That energy could have spun a turbine blade and generated electricity you could sell to the grid. Instead, you degraded it into useless, low-grade warmth in the atmosphere. You can never, ever get that capacity back. Entropy generation isn't a measure of a messy room. It is a measure of destroyed financial and mechanical potential.
Let me give the listener an analogy to lock this in. Think of a heavy mass suspended on a thick steel spring. You pull the mass down and let it go.
Okay, simple harmonic motion.
Right. In a perfect reversible world, that mass oscillates up and down forever, returning exactly to its starting peak every single time.
Right.
But in the real physical world, it doesn't. Every time the spring stretches, the internal metallic bonds rub against each other, creating microscopic internal friction. This generates a tiny bit of heat within the steel.
Yes.
Furthermore, as the mass moves up and down, it is physically slamming into air molecules, pushing them out of the way, creating aerodynamic drag.
Both of which are completely irreversible.
Exactly. Both the internal friction and the air drag are irreversible. They generate entropy. And because of that entropy generation, the mechanical energy of the bouncing mass is slowly converted into useless ambient heat. The bounces get shorter and shorter until the mass comes to a dead stop.
Left alone, entropy always wins.
Always. To make that mass bounce endlessly, the environment, meaning a human or a motor, must actively intervene and do physical work on the system to replace the destroyed exergy.
And bringing this back to heavy machinery, this irreversible reality causes massive design headaches. Because the math of real irreversible processes is so incredibly complex, engineers frequently design systems by assuming the processes are reversible and adiabatic.
Adiabatic meaning perfectly insulated, zero heat transfer.
Exactly. And reversible meaning zero friction. We combine these two assumptions into an ideal state called an isentropic process, meaning entropy remains perfectly constant from the inlet to the outlet.
It makes the math beautifully simple. You just set S1 equal to S2 and solve for your exhaust property.
It's very tempting.
But when you actually build the turbine and bolt it to the test stand, the real kinetic energy and the real exhaust temperatures are wildly different from your isentropic calculations. Why? How does friction literally change the physical speed of the gas?
This is the physical chain reaction of entropy. Let's walk through a real turbine. As the high-pressure gas expands through the spinning blades, fluid friction occurs. The gas molecules rub against the microscopic roughness of the titanium blades, and turbulent shear layers rub against each other.
Lots of rubbing.
Tons of it. This friction acts like a microscopic heater inside the fluid, generating waste heat.
Okay.
Because of this internally generated heat, the gas at the exhaust is physically hotter than it would have been in your perfect isentropic fantasy. And what happens when a gas is hotter?
It expands.
Yes, it expands. Its specific volume, V, increases.
Oh, I see where this is going.
Now remember that this is a steady flow machine. Mass flow rate is constant. You have a larger, hotter, fatter volume of gas that must be forced through the exact same physical cross-sectional area of the turbine exhaust casing.
Because the metal doesn't grow.
Exactly. To shove a larger volume of fluid through a fixed area in the same amount of time, the fluid must physically accelerate to a higher velocity.
So the actual kinetic energy of the gas leaving the turbine is altered strictly because the specific volume increased due to entropy generation. Your beautiful isentropic assumption blinded you to how the physical fluid reacts to its own internal friction.
Exactly. Assuming constant entropy blinds you to the physical swelling of the gas.
Which is the perfect bridge into our next major pillar, Section 3, governing the flow. We understand the energy tracking, and we understand the brutal tax of entropy. But how do we actually track the physical mass of the fluid as it swells, accelerates, and navigates through a labyrinth of pipes and compressor blades?
We need governing rules.
Right. We need governing rules for the flow itself.
And the absolute foundation of fluid tracking is the equation of continuity. It is the mathematical statement of the conservation of mass.
Keep track of this stuff.
Keep track of the stuff. Simply put, mass cannot magically vanish into the ether, and it cannot spontaneously appear out of nowhere. If you have a steady one-dimensional flow moving through a pipe, the mass flow rate must be identical at every single cross-section of that system.
The equation is m dot equals density, rho, multiplied by the normal velocity, c sub n, multiplied by the cross-sectional area, a. So m dot equals rho times c times a.
Think about a river that is flowing wide and slow. Suddenly, it enters a narrow, rocky gorge.
Okay.
The total amount of water moving down the mountain hasn't changed. M dot is constant. Liquid water is basically incompressible, so its density, rho, stays constant.
Right, water doesn't compress much.
Therefore, mathematically and physically, if the area A shrinks, the velocity, C, must massively increase to push the same amount of mass through the bottleneck. The water speeds up and becomes a violent rapid.
It's the exact same principle as putting your thumb over the end of a garden hose.
Oh yeah, perfect example.
You decrease the area, the velocity spikes, and the water shoots across the yard. Now that explains that it accelerates. But what are the physical forces causing that acceleration? That requires applying Newton's second law to a moving fluid.
When you look at a solid block sliding down a ramp, you use force equals mass times acceleration. But fluids deform continuously. We can't track a single solid block.
It's all squishy.
Exactly. Instead, we use the momentum equation. It states that the sum of all external pressure and body forces acting on a specific control volume of fluid equals the time rate of change of momentum of the fluid passing through it.
Okay.
If you take this momentum principle, combine it with the conservation of mass, and look at an idealized scenario where there is no viscous friction and no spinning shafts doing work, you arrive at Euler's equation of motion.
And Euler's equation is famous because of what happens when you integrate it. If you integrate Euler's equation along a single streamline of flow, you give birth to the most famous, most tattooed equation in all of engineering, the one that every student spends weeks deriving, Bernoulli's equation.
Yes, Bernoulli, the integrated form of Euler's equation. It states that the static pressure of the fluid divided by its density plus 1/2 the fluid's velocity squared plus gravity times height equals a constant value anywhere along that streamline.
P over rho plus 1/2 c squared plus gz equals a constant. It is a brilliant, elegant statement of the conservation of mechanical energy.
Truly elegant.
And tied directly to Bernoulli is a concept that is critical for aerodynamicists and turbine designers, stagnation pressure, or total pressure. The equation for this is P0 equals P plus 1/2 rho times c squared. What does stagnation actually represent physically?
To feel stagnation pressure, just think about driving down the highway at 70 miles per hour and sticking your hand out the window, palm facing forward.
We've all done that.
Right. The ambient air you are driving through has a specific static pressure. It's the normal weight of the atmosphere. It also has a relative velocity approaching your hand. But when that air physically impacts the center of your palm, it cannot pass through your skin. It is forced to come to a complete dead stop. Its velocity drops to 0.
So where does the energy go?
According to Bernoulli, the kinetic energy of that moving air doesn't just vanish. As the air decelerates against your hand, that kinetic energy is entirely transformed into pressure.
Wow.
The heavy, forceful pressure you feel pushing your arm backward is the stagnation pressure. It is the sum of the ambient static pressure plus the dynamic pressure, that 1/2 root c squared term. Stagnation pressure represents the absolute maximum pressure you could achieve if you took a moving fluid and brought it to a complete reversible halt.
It is the total energy cache of the fluid. Now here's where we have to talk about a massive career-ending trap. I hear this from junior engineers who fall in love with the elegance of Bernoulli. The math is so simple, just basic algebra. And they ask, can I use Bernoulli to calculate the pressure drop across the compressor stages of a jet engine?
And the answer must be a resounding aggressive no. This is one of the most catastrophic mistakes you can make in fluid mechanics. You absolutely cannot use the standard Bernoulli equation for a high-speed gas turbine or a high-pressure compressor.
But why not? The equation works perfectly for water pipes. Why does it fail for a jet engine?
Because of one lethal, hidden assumption baked into the integration of Bernoulli's equation: constant density. The equation assumes that the density of the fluid, ratio, never changes. This works beautifully for liquid water because water is virtually incompressible. You can squeeze it with thousands of pounds in pressure and its density barely shifts. Bernoulli also works acceptably well for air moving at very low speeds, like the airflow from a desk fan or the aerodynamics of a slow-moving Cessna aircraft. The pressure changes are so small that the air density essentially remains constant.
But inside a jet engine.
Inside a jet engine compressor, the air is being violently smashed into smaller and smaller volumes. It is being compressed to 30 or 40 times atmospheric pressure, and the temperature is skyrocketing. The density, rho, is changing drastically and continuously across every single millimeter of the machine.
So if you use Bernoulli,
If you attempt to use the incompressible Bernoulli equation on a high-speed, highly compressible gas, your mathematical predictions will deviate from reality by massive margins. Your pressure calculations will be wrong, your structural load calculations will be wrong, and your engine will stall or rip itself apart.
makes.
When density changes, you must abandon Bernoulli and use the full compressible flow equations, which require incorporating thermodynamic properties like specific heat capacities and absolute temperatures to track exactly how the gas is squeezing and swelling.
Do not use water math on high-speed air. That is the takeaway.
Pure.
All right, so we have laid out the overarching laws. We know how energy is tracked, we know the brutal taxes of entropy, and we know the rules for tracking the fluid's mass and momentum. But equations on a chalkboard don't spin generators. Hardware does. We need to take these physics and slam them into real steel. Let's walk into section 4, the engine room. Let's break down the actual components mechanical engineers design and troubleshoot every day.
Let's start with the most basic component in any piping system, valves and throttles. A valve is fundamentally just a physical restriction, a bottleneck in a pipe.
Okay, so what happens to the fluid's energy when it forces its way through a partially closed valve?
First, let's look at the first law. There is no spinning shaft attached to a valve, so there is zero mechanical work being done. And because the fluid blasts through the restriction so incredibly fast and the surface area is relatively small, there is no time for heat to transfer to the environment.
So dq is 0 and dw is 0.
Right.
If we look at our steady flow energy equation and we assume the inlet and outlet pipes are the same size, so kinetic energy doesn't change drastically, the first law dictates a very specific outcome. The total enthalpy of the fluid at the inlet must perfectly equal the total enthalpy at the outlet. H1 equals H2. This is called an isenthalpic process.
Correct. The pure energy content remains identical. But do not confuse constant energy with a harmless process. What does the second law say?
Entropy tax.
Exactly. Forcing a high-pressure fluid through a tiny restrictive gap creates massive, violent turbulence. The fluid shears against itself, creating immense internal friction. Therefore, entropy generation is strictly heavily positive.
Right.
As the fluid expands through the valve, its pressure plummets. So while the total enthalpy is conserved, the availability of that energy, its exergy, its potential to do useful mechanical work, is permanently degraded. You took high-pressure, highly organized fluid that could have spun a turbine, and you turned it into low-pressure, highly disordered fluid.
And you can never get that pressure back without plugging a compressor into the wall and consuming external electricity.
Yes.
Valves destroy potential.
Yes. They destroy potential.
Next on the floor, turbines and expanders. These are the absolute powerhouses of human civilization. Whether it's steam in a nuclear plant or hot gas in a jet engine, the goal is the same.
The goal of a turbine is to extract enthalpy. A high-pressure, high-enthalpy fluid expands through rows of specifically shaped spinning aerodynamic blades. Again, because the velocities are so high, we generally model them as adiabatic, meaning negligible heat loss to the casing.
Okay.
The entire purpose of the machine is to produce work. So, applying the first law, the mechanical shaft work produced is equal to the mass flow rate multiplied by the physical drop in the fluid's enthalpy.
Yeah.
W equals m dot times the difference between H1 and H2.
Wow, just basic subtraction when you get down to it.
Right. The fluid enters violently hot and highly pressurized. It does massive flow work pushing against the spinning blades, and it leaves the exhaust relatively cold and at low pressure. That difference in enthalpy is what spins your generator and powers the electrical grid.
And the exact mirror image of a turbine is our third component category, compressors and pumps.
Exactly. If a turbine extracts enthalpy to produce work, a compressor consumes work to force enthalpy into the fluid. You supply electricity to a massive external motor to spin the compressor blades.
So it's backwards.
Completely backwards.
Right.
These blades violently strike the fluid, forcing it into a smaller volume and raising its pressure and temperature. The mathematical work consumed equals the mass flow rate times the rise in enthalpy. The environment is actively doing work on the system.
Now let's look at nozzles and diffusers. These always blew my mind as a student. They're essentially just shaped metal tubes. Like a valve, there are absolutely no moving parts, no spinning shafts, therefore no work is done.
Nope, no work.
And heat transfer is negligible. But unlike a valve, their entire design purpose is to manipulate the velocity of the fluid.
A nozzle takes a slow-moving, high-pressure fluid and accelerates it to immense speeds. It is a thermodynamic exchange machine. It trades enthalpy for kinetic energy.
Okay, walk us through that.
As the fluid forces its way through the converging, narrowing shape of the nozzle, continuity dictates it must speed up. As its velocity increases dramatically, the first law dictates that this kinetic energy must come from somewhere. It comes from the fluid's internal energy and flow work. The static pressure and the enthalpy drop correspondingly.
That makes total sense.
A diffuser does the exact mathematical opposite. It takes a high-velocity fluid and gradually slows it down by expanding the cross-sectional flow area. As the fluid slows, its kinetic energy drops. That kinetic energy doesn't disappear. It is converted back into a rise in enthalpy and a rise in static pressure.
This simple exchange of enthalpy for kinetic energy is the entire basis of how a jet engine generates thrust. The core of the jet engine, the compressor, combustor, and turbine, exists purely to generate extremely high-pressure, high-enthalpy gas. Then, a massive converging nozzle at the very back of the engine trades all of that stored enthalpy for pure, high-speed kinetic energy shooting out the rear.
Pure genius.
By Newton's third law, that massive rearward kinetic momentum propels the multi-ton aircraft forward. No moving parts of the nozzle, just pure thermodynamic conversion.
And finally, we must discuss the unsung heroes of the thermal world. Heat exchangers. Radiators, condensers, evaporators, boilers. These are devices designed specifically to transfer heat energy from a hot fluid stream to a separate cold fluid stream, usually through conductive metal walls, without the two fluids ever physically mixing.
And bringing up heat exchangers forces us to confront a massive, widespread misconception. When students or junior engineers model a heat exchanger in a thermodynamic cycle, like a Rankine steam cycle, they almost always draw a perfectly horizontal line on the pressure-volume diagram. They assume the pressure of the fluid remains perfectly constant from the inlet of the heat exchanger to the outlet. P in equals P out.
Oh, I see this all the time. I cannot emphasize enough how dangerous and costly that assumption is when you transition from the classroom to the real world. I must call this out explicitly. A pressure drop always occurs in the direction of flow inside any real heat exchanger.
Why is it unavoidable?
Think about how a heat exchanger is built. To maximize heat transfer, you have to maximize surface area. So you force the fluid through hundreds of miles of incredibly narrow tubes, or zigzagging over corrugated metal plates, or past thousands of tiny, densely packed fins.
You're basically creating a physical obstacle course for the fluid.
Exactly, an obstacle course. And that obstacle course creates immense fluid friction and aerodynamic drag. To force a fluid to overcome that friction and keep moving forward, you must have a high pressure at the inlet pushing toward a lower pressure at the outlet. Friction demands a pressure differential.
So if you ignore it.
If you design a massive chemical plant and ignore the pressure drop across your heat exchangers, your entire system will fail on day one. The physical pump or compressor pushing the fluid through that exchanger will have to work significantly harder, drawing massively more electrical current than your idealized constant pressure math predicted. Your efficiency calculations will be ruined, and your motors will likely burn out. The real world has friction. You must account for the pressure drop.
That is the difference between passing a thermo exam and actually keeping a refinery online. All
Complete.
right, so throughout this entire discussion, we've been relying on a hidden crutch. We've been assuming our fluids behave nicely. We've been assuming they follow simple mathematical rules. But nature absolutely hates being put in the box. Fluids are messy. Molecules interact. This brings us to section 5. Ideal gases versus real fluids. When do fluids stop acting ideal?
Well, to understand when they break the rules, we first have to define what the rules of an ideal gas actually are. The most famous equation of state in physics is the ideal gas law. P times V divided by T equals R, where R is the specific gas constant for whatever fluid you are using.
We all know that one.
But for that beautiful, simple equation to work, it makes two massive fictional assumptions about reality. First, it assumes that the gas molecules are infinitesimally small point masses, that they take up exactly zero physical volume themselves.
Which is impossible.
Right. Second, and more importantly, it assumes that these molecules exert absolutely zero electromagnetic attractive forces on one another.
They are essentially modeled as microscopic, perfectly hard billiard balls that bounce perfectly off the container walls and each other with no stickiness whatsoever.
Exactly. And tied intimately to the ideal gas law are the specific heats. We have C sub P, the specific heat at constant pressure, and C sub V, the specific heat at constant volume. These values tell us how much thermal energy it takes to raise the temperature of 1 kilogram of the gas by 1 degree.
Now, a classic interview question for mechanical engineers is, why are there two different specific heats for gases? And why is C sub P mathematically always greater than C sub B?
Oh, that's a good one. It comes back to flow work and boundary work. Imagine heating a gas that is trapped inside a rigid, sealed, heavy steel tank. The volume cannot change. That is constant volume. When you add a blowtorch to the tank, 100% of the heat you add goes directly into increasing the internal kinetic energy of the molecules. It all goes into raising the temperature. That is C sub B.
Okay, all heat becomes temperature.
Right. Now, imagine heating that same gas, but this time it is inside a cylinder capped with a heavy sliding piston. The piston maintains a constant pressure on the gas. As the gas heats up, it expands. And as it expands, it physically pushes that heavy piston upward against the weight of the atmosphere.
It's doing mechanical work on the environment.
Exactly. In this constant pressure scenario, the heat you add from the blowtorch is forced to do two distinct jobs. It must raise the internal temperature of the gas, and it must provide the mechanical energy required to push that heavy piston upward. Because the heat is split doing two jobs, it takes more total heat to raise the temperature of the gas by 1 degree. Therefore, C sub B must always be numerically greater than C sub V. The difference between them is exactly the boundary work done by the expansion.
But again, the ideal gas law is a mathematical fiction. Real molecules are not point masses. They do take up physical space, and they are absolutely sticky. Water molecules, for example, are highly polar. The oxygen and hydrogen atoms create magnetic poles that desperately want to attract and stick to other water molecules. When fluids get cold or highly compressed, they are shoved so close together that these idealized assumptions completely collapse.
Which is why brilliant physicists spent decades developing more complex, realistic equations of state. Equations like the van der Waals equation or the Dieter-Ricci equation. These mathematical models attempt to fix the glaring flaws of the ideal gas law.
How do they fix it?
Well, van der Waals, for instance, introduced two specific corrective constants to the equation, universally referred to as A and B. The A constant is a mathematical correction for intermolecular attraction. It accounts for the fact that as molecules approach the wall of a container, the other molecules behind them are magnetically pulling them backward, which effectively reduces the actual pressure they exert on the wall.
Interesting. And the B constant?
The B constant is a geometric correction. It accounts for the actual physical chunkiness of the molecules. Because the molecules themselves take up physical space, the actual empty void volume available for them to fly around in is significantly less than the total volume of the steel tank.
And understanding how these real fluids behave becomes absolutely critical when you push a fluid toward its critical point. Let's explain this to the listener because it sounds like sci-fi. Every pure substance in the universe has a specific critical temperature, Tc, a critical pressure, Pc, and a critical specific volume, Vc. What physical madness happens at this exact thermodynamic coordinate?
Oh, it is madness. At the critical point, the fundamental distinction between what we call a liquid and what we call a gas completely and utterly breaks down.
Wait, really?
Yes. If you are at normal atmospheric pressure below the critical point and you heat liquid water, you witness a distinct phase change. You see boiling. You see a physical, visible surface boundary separating the heavy, dense liquid water at the bottom of the pot from the light, invisible steam floating above it.
Like making pasta.
Exactly like making pasta. But if you put that water in an ultra-high pressure vessel and you compress it to a pressure higher than its critical pressure, which is over 3,200 psi for water, and then you heat it, it never boils.
That just doesn't boil.
It never boils. You never see bubbles. You never see a surface boundary. The fluid just continuously, seamlessly morphs from a highly dense fluid into a less dense fluid. There is no phase change. The fluid exists in a state that defies the simple binary categories of liquid or gas.
That is wild. And studying this critical point gave us something incredibly useful, right? The law of corresponding states. Based on van der Waals' work, scientists realized that if you normalize any fluid's current pressure, temperature, and volume by dividing them by their absolute critical values, creating a ratio we call reduced properties, a fascinating pattern emerges. Whether it is nitrogen, methane, or water, all fluids will behave roughly the same way at the same reduced properties. It proved that the deviations from the ideal gas law are universally tied to how close a substance is to its critical point.
It is a profound realization of universal symmetry. However, For daily, boots-on-the-ground engineering work, complex equations like van der Waals are often too mathematically cumbersome or simply too imprecise for highly complex mixtures or fluids nearing condensation.
So what do we do instead?
That is why, in practice, we rely heavily on empirical thermophysical property tables. If you are designing an industrial refrigeration system using R134a or a modern eco-friendly heat pump using supercritical carbon dioxide, you do not calculate the enthalpy from an equation of state. You look it up in meticulously experimentally derived data tables.
Especially because these machines operate deliberately inside the two-phase region. That's the area underneath the saturation dome on a thermodynamic chart where the fluid is actively boiling or condensing, a chaotic mixture of liquid and vapor. Inside that dome, properties like specific volume, enthalpy, and entropy change drastically, non-linearly, and completely independently of temperature.
Exactly. The math breaks down entirely under the dome.
But let me push back here on behalf of the students who just spent a semester learning PV equals RT. If the ideal gas law is a fiction, if it ignores the physical chunkiness of molecules, if it ignores intermolecular magnetic attraction, and if we have access to massive databases of highly accurate empirical tables, why do we still teach the ideal gas law? Why are we using a flawed equation?
Because context is everything in engineering. The ideal gas law is flawed, yes, but in a very specific, very common thermodynamic regime, it is incredibly accurate and infinitely faster than interpolating massive data tables.
Okay, what regime?
The ideal gas law works beautifully at high temperatures and low pressures. Think about the air intake of a jet engine cruising at altitude. The air is at a low atmospheric pressure, and once inside the engine, it gets incredibly hot. Under these conditions, the gas molecules are moving at blistering speeds, and because of the low pressure, they're physically very far apart from one another.
So they're moving too fast, and they are too far apart for their magnetic stickiness to grab hold of each other.
Precisely. And because they are so far apart, the physical volume of the molecules themselves becomes mathematically insignificant compared to the vast empty space between them. In that specific high-temp, low-pressure regime, the A and B corrections of van der Waals effectively drop to zero. Real gases behave almost exactly like ideal gases. The simple math is highly accurate.
Right.
However, the ideal gas law will fail catastrophically if you attempt to use it near the saturation line, where the gas is cold and dense and about to condense into a liquid. A master engineer knows the limitations of their tools. You use PV equals RT to calculate the airflow through a wind tunnel. You absolutely never, ever use it to calculate the state of the boiling refrigerant moving through the evaporator coils of your home air conditioner.
That right there is the masterclass difference, knowing exactly when the rules apply and when the physical reality breaks them.
You have to know.
So we know how to track the fluids, we know when they act perfectly, and we know when they act like real sticky molecules. This brings us to section 6, the efficiency illusion. If we design a massive multi-stage turbine, how do we grade its performance? To know if a machine is good, we have to compare it to a standard of perfection. But as we discussed earlier with entropy, perfection is a moving target depending entirely on how you define your boundaries.
And the most universal metric we use to grade turbomachinery is isentropic efficiency. We look at the actual mechanical work a machine produced, and we divide it by the theoretical work it would have produced if the expansion had been perfectly reversible and adiabatic. If the entropy had remained perfectly constant. It is a ratio of reality versus theoretical perfection.
But even within that ratio, there is a massive debate that causes endless confusion. Let's talk about total to total isentropic efficiency versus total to static. This hinges entirely on how we treat the kinetic energy of the fluid exhaust. When steam leaves a turbine blade, it is moving fast. It has significant kinetic energy. Is that exhaust velocity considered wasted energy, or is it useful energy?
It completely and utterly depends on the physical application of the machine. Let's look at a massive standalone steam turbine in a coal or nuclear power plant. The sole purpose of that turbine is to spin a copper generator to make electricity.
Okay.
Once the steam leaves the very last row of aerodynamic blades, any forward velocity it still possesses is entirely useless. It just shoots into the massive void of the condenser and slams into the cooling tubes. It doesn't help spin the shaft.
So it's waste.
In that specific context, the exhaust kinetic energy is pure waste. Therefore, we evaluate that machine using a total to static efficiency metric. This metric strictly penalizes the turbine's grade for leaving unextracted kinetic energy in the exhaust stream.
But what if that exact same turbine geometry was bolted onto the back of a military fighter jet?
then the rules of the game change entirely. If it is the final turbine stage of an aircraft jet engine, that high-speed exhaust kinetic energy isn't waste at all. It is the entire point of the machine. That high-velocity exhaust is the propulsive thrust keeping the jet in the sky.
Wow.
Or consider an intermediate stage in a multi-stage turbine. The high-speed fluid exiting stage 1 shoots directly into the inlet guide vanes of stage 2. That velocity isn't lost, it is highly useful input energy for the next row of blades.
So you don't penalize it.
Exactly. In both of those cases, we use total-to-total isentropic efficiency. This metric mathematically credits the machine for the kinetic energy remaining in the exhaust, treating it as a highly useful output rather than a thermodynamic loss. You have to draw your control volume carefully and understand the physical intent of the machine.
That makes perfect sense. Context dictates the metric. But here is where the math of efficiency plays a cruel, hidden trick on engineers. Let's dive into the hidden thermodynamic effect, which is also commonly known as the preheat effect in compressors or the reheat effect in turbines.
Oh, this is a mind bender.
It absolutely is. This concept is just mind-blowing when you first encounter it. The mathematical truth is this. The overall isentropic efficiency of a finite multi-stage compressor is always less than the isentropic efficiency of its small individual stages. If every individual row of blades is 90% efficient, the overall 10-stage compressor will somehow be less than 90% efficient. Why does the math penalize the whole machine?
It goes directly back to our discussion of entropy, friction, and waste heat. Let's carefully walk through a large compressor made of 10 individual stages, 10 rows of spinning blades.
Okay, visualizing that.
As the air gets violently compressed through stage 1, fluid friction generates waste heat. This is irreversible entropy generation. Because of this internally generated waste heat, the air entering stage 2 is physically hotter than it theoretically should have been.
Right.
Now, recall the first law boundary work principle we discussed with specific heats. The mechanical work required to compress a gas is directly proportional to its specific volume. Pushing a large, hot, swollen volume of gas takes significantly more mechanical work than pushing a small, cold, dense volume of gas.
So the aerodynamic inefficiency of stage 1 generates heat, which swells the gas, making the actual physical job of compression harder for stage 2.
Exactly. Stage 1's thermodynamic failure makes stage 2's mechanical job fundamentally harder. And then stage 2 generates its own frictional heat, compounding the problem and making stage 3's job even harder. The heat penalty compounds exponentially down the line.
So it snowballs.
It snowballs. Because of this compounding thermal penalty, the overall isentropic efficiency of the entire 10-stage machine will calculate out to be lower than the aerodynamic efficiency of the individual blade rows. The overall metric is mathematically polluted by the thermodynamics of heating.
And this hidden thermodynamic effect leads to a massive, real-world pain point that catches junior engineers constantly. Imagine you are a lead engineer on a new chemical plant. A vendor comes into your office pitching 2 different industrial compressors. Compressor A is a standard machine with a moderate pressure ratio of 5:1. Compressor B is an absolute beast. It has a massive pressure ratio of 20:1.
I've seen this play out so many times.
The young engineer takes the vendor's spec sheets, calculates the overall isentropic efficiencies, and sees that the high-pressure compressor B has a lower overall isentropic efficiency score. They immediately conclude that compressor B is a poorly designed machine built with inferior aerodynamic blade profiles.
And that conclusion is entirely mathematically invalid. It is a completely unfair comparison.
Because of the snowball effect.
Exactly. Compressor B is being heavily penalized by the hidden thermodynamic effect simply because it compresses the gas to a much higher pressure, thereby generating vastly more compounding waste heat across a larger number of stages. Compressor B might actually have vastly superior, highly advanced blade aerodynamics compared to compressor A. But the overall isentropic efficiency metric completely masks that aerodynamic brilliance because it is overwhelmed by the thermodynamic heat penalty of the 20:1 compression ratio.
So how do you actually compare them fairly? If isentropic efficiency lies to us across different pressure ratios, what metric do we use to see the true aerodynamic quality of the blades?
You must abandon isentropic efficiency and use polytropic efficiency.
Polytropic efficiency.
Polytropic efficiency is a brilliant mathematical workaround. It essentially takes the compressor and mathematically slices it up into an infinite number of infinitesimally small compression stages. By doing this, it completely removes the compounding heat penalty from the equation. Polytropic efficiency reveals the true, unpolluted aerodynamic quality of the machine, completely independent of its overall pressure ratio.
If you are comparing machines with different pressure ratios, you must use polytropic efficiency. That is a multi-million-dollar nugget of practical engineering wisdom.
It really is.
All right, we are entering the final stretch. Section 7, answering the internet's biggest questions. We scoured the engineering subreddits, the mechanical forums, the dark corners of the internet, where engineers go at 2 a.m. when their CFD simulations are crashing and their real-world hardware is failing on the test stand. We are going to take the factual, thermodynamic principles we've discussed today and use them to definitively answer the most common points of confusion.
Let's address the pain points. I am ready.
Question number 1. This is a classic, desperate plea from the forums. Why is my real-world compressor drawing significantly more electrical power than my simple P times V equals R times key calculation predicted? My math says I only need a 100 horsepower motor, but the actual physical compressor on the floor is tripping the 150 horsepower breaker. What went wrong?
Well, if you have been following this masterclass, we have already provided all the puzzle pieces to solve this mystery. If you sized your motor using PV equals RT, you made two massive, highly idealized assumptions that reality is actively punishing you for.
Which are?
First, you assumed the gas behaves like a perfect ideal gas. But if you are compressing an industrial fluid to very high pressures, or if the fluid is particularly cold, you might be nearing the saturation dome. You are entering a state where the actual physical compressibility of the fluid changes drastically. The physical volume of the gas is different than your simple equation predicted, which alters the flow work required.
And the second assumption?
Second, and far more importantly, your simple calculation assumed a 100% reversible isentropic compression process. You mathematically assumed there was zero friction.
They ignored the taxman.
Exactly. In reality, your compressor is violently thrashing the fluid. It is generating massive amounts of entropy through mechanical bearing friction, aerodynamic turbulence over the blades, and heat loss through the heavy steel casing. You failed to account for the Gauss-Stodelith theorem.
So that extra 50 horsepower.
That extra 50 horsepower your electric motor is desperately drawing from the grid. That is the physical electrical manifestation of T0 times Sgen. It is the real-world financial penalty for irreversibility. You cannot use a theoretical ideal calculation to size real hardware. You must use the empirical isentropic or polytropic efficiency of that specific compressor model to scale up your theoretical ideal work to find the actual brutal shaft work reality demands.
Beautifully explained. It's always the entropy tax. Question number 2. We touched on this during the efficiency discussion, but let's make it crystal clear for the aeronautical guys.
Yeah.
Does kinetic energy at the exhaust of a turbine always hurt my system's overall efficiency?
No, absolutely not. Context is the supreme ruler of thermodynamics. If you are designing a massive standalone steam turbine in a geothermal plant and it exhausts directly into a gigantic stationary cooling condenser, then yes, any residual velocity in that steam is wasted kinetic energy. It could have been extracted by adding one more row of blades to spin the shaft.
Right.
But if you are designing the high-pressure turbine of a military turbofan engine, that exhaust kinetic energy is emphatically not waste. It is the entire functional output of the engine. It is your jet thrust. Or if you are doing thermodynamic analysis on a 15-stage industrial compressor, the high-speed exit velocity of stage 4 is the required inlet kinetic energy for stage 5. It isn't wasted. It is simply passed sequentially down the thermodynamic line.
You just have to know your boundaries.
You must draw your mathematical control volume boundary with extreme care, and you must understand the specific engineering purpose of the fluid's kinetic energy at that exact location in the machine.
And finally, question number 3. This one comes constantly from HVAC engineers, refrigeration technicians, and anyone designing thermal management systems. How do I avoid getting completely lost in the massive thermophysical property tables for refrigerants like R134A? There are hundreds of pages of numbers, and none of them seem to follow a simple equation. How do I know which number to pick?
Surviving the property tables requires absolute respect for the thermodynamic phase boundaries. You must always, always check your physical pressure and your physical temperature against the saturation lines first.
Always check where you are.
Yes. If your measured temperature is higher than the boiling point for your given pressure, you are in the superheated vapor regime. You go to the superheated tables where the fluid acts relatively close to a normal gas. If your temperature is lower than the boiling point, you are a subcooled liquid.
But the trap is the saturation line.
Exactly. If your pressure and temperature match exactly on the saturation curve, you are trapped underneath the thermodynamic dome. You are dealing with a violent two-phase mixture of boiling liquid and expanding vapor.
And under the dome, pressure and temperature are completely locked together. Knowing the temperature tells you absolutely nothing about how much energy is in the fluid, because it could be 1% vapor or 99% vapor at that exact same temperature.
Precisely. When you are under the dome, to find your actual enthalpy and your actual entropy, you must calculate a property called quality. Quality, usually denoted by the letter X, is the strict mathematical ratio of the mass of the vapor to the total mass of the mixture.
Okay, so you find the X.
Once you calculate the exact quality, you use it as a percentage to mathematically interpolate between the pure liquid enthalpy value and the pure vapor enthalpy value listed in the tables. If you don't calculate the quality, you are flying completely blind in the two-phase region, and your refrigeration cycle calculations will be completely worthless.
Find the quality. Find your enthalpy. That is how you survive the dome. We have covered incredible ground in this masterclass today, from the absolute foundations of the first and second laws, through the physical reality of enthalpy and the brutal taxes of entropy generation. We've exposed the limits of Bernoulli's equation, explored the hidden thermodynamic penalties of high-pressure compressors, and navigated the messy, sticky reality of real-world fluids and two-phase refrigerants.
It's a lot, but it's the foundation of everything we build.
It is. But I want to leave you, the listener, with one final, provocative thought to mull over as you step back out into the real world. We talked about the critical point, that bizarre thermodynamic coordinate where the math of van der Waals starts breaking down and the distinct line between a liquid and a gas completely blurs.
Yeah.
But what happens if you push a fluid way, way past that critical point? You engineer something called a supercritical fluid. It is one of the most bizarre states of matter in the universe. It physically expands to fill its container exactly like a gas, but it retains the dense, heavy, dissolving power of a liquid.
It's honestly incredible.
It sounds like a physics anomaly, but it is the absolute frontier of modern engineering. Today we use supercritical water, operating at mind-boggling pressures and temperatures, to drive the most advanced, ultra-efficient power generation turbines on Earth. And on the complete opposite end of the spectrum, we use supercritical carbon dioxide as a massive industrial solvent to naturally dissolve and extract caffeine from coffee beans without leaving behind any toxic chemical residues.
From turbines to decaf coffee.
Yes, exactly. All of this world-changing, cutting-edge technology was born simply from engineers aggressively pushing the extreme limits of the pressure, volume, and temperature surface we explore today. These equations aren't just dry math on a page, they're the literal blueprints for controlling the physical universe. If this helped you even a little, say something. We're putting this out for free, no paywall, no subscription, nothing locked behind a card. That only works if we know it's actually reaching people and doing what it's supposed to do. If you're a young engineer trying to figure this stuff out and this gave you clarity you weren't getting anywhere else, drop a like, leave a comment. It takes 2 seconds on your end, but it tells us this is worth continuing instead of just talking into the void. We're excited for your feedback, negative or positive.